Swayam Prabha. Digital India. Educated India.
All right, welcome back. So we were talking about the localized surface plasmons. So how do we excite the localized surface plasmon? Well, there are multiple ways of doing it, and one of the ways is actually to excite by what is known as dark field microscopy. Okay, so what we can do is we can have a microscope, and you shine light at an angle, at a high angle, so that most of the incident light gets reflected, and you don't see the reflected immediate direct reflection, but whatever gets scattered you can see. For example, what we can do is take this is a image taken using what is known as dark field microscopy. So you have these metal nanoparticles which are dispersed on a glass slide, and you look at it in the dark field mode. Okay, and that is why it's called as dark field, because the background looks dark, because the direct reflections are eliminated in the microscope. There's a small type of objective different type of objective you have to use. If you use that, essentially the direct reflections are eliminated and you end up getting only the scattered light. And that's why it's called dark field. And in contrast, the regular bright field microscope is what is shown in the bottom. Okay, wherein you can see these specks, which are basically these nanoparticles, but we don't see them clearly because there's a strong background. Okay, so the incident light is actually much stronger. So that's one of the challenges of plasmonic resonances. So we have these resonances which are very strong, but if we have a single nanoparticle, we have to take a lot of precautions to actually observe it. Okay, like for example, this dark field excitation. If you do that, you see these nanoparticles of different colors. The reason the colors are coming is each nanoparticle is of a different size and it has a different resonant wavelength. And because of that, it efficiently, this particle will efficiently excite or scatter red, and this will scatter, let's say, green and blue and so on. Okay, so you have these different types of different resonant wavelengths which will cause this scattering. Okay, and you might ask, where is the size dependence coming in? For example, in the quasi-static limit that I have shown in the previous lecture, you see that there is no size dependence here. The surface charge or polarization is essentially only dependent on the permittivity. There is no size dependence. So where is this coming from? Well, it turns out that as you go to this quasi-static description is truly valid when you have very small size nanoparticle. But the moment the size becomes large, you see that the quasi-static limit breaks down. What does it mean when we say that quasi-static limit breaks down? Well, the electric field is no longer constant over a nanoparticle. It can have a variation, and that can lead to shifting of resonance. Okay, so the ideal approximation that the electric field is constant all across a nanoparticle breaks down. All right. You can also have different resonant wavelengths because of changes in the geometry. Okay, so we considered a simple nanosphere, okay, which is the simplest object. And if you actually look at the textbook, you'll see that the solution also involves a lot of mathematics. But the moment you have, let's say, triangles and pentagons and this different shapes of nanoparticles, which by the way we can actually fabricate in the labs. Okay, the chemistry of these nanoparticles has become very advanced, and people actually can control the shapes very well. Let's say if you have nanoparticles of different shapes like this, because of the shapes there is different resonant wavelengths. And what I mean by resonant wavelength is that you see this peak in, this is a scattered light, right? So peak in scattered light, okay, scattered light exhibits peak at different wavelengths. So you see that if you look at the scattered light mode, you'll see that the color is different for each of these nanoparticles. It can happen. And there is no easy way of understanding this size dependence of the nanoparticles. Okay. So I said that, okay, the quasi-static limit breaks down. So what? Why should, why should the, let's say in this case, I'm showing you the analytical calculations done by using what is known as me theory. Me theory, analytical. Me theory is a technique that is given by Gustav Mee, I think in 19th century. He calculated what happens, when you have light incident on these nanoparticles, and then what you can actually compute it, and we'll actually put the code for this on GitHub. We'll probably also try to have a small demo of that so that you can try it out. So essentially, if you do these calculations, in this case, I think this is done for a silver nanoparticle of different diameters. Okay, Ag nanoparticle of different diameters going from 50 nanometers to 150 nanometers. When you have this range of nanoparticles, you see that the scattering cross section, basically how efficient is this in scattering? Let's say if you have a nanoparticle, how much is the scattering cross section? So we said that already this is a resonant phenomena, right? So for example, if I take a nanoparticle of this part size, the physical size, the cross section is, let's say, pi r square. If that r is the radius of the particle, then the pi r square is the cross section. But because of the resonance, effectively the particle is able to scatter light much better. The scattering cross section is greater than 1. Okay, if I normalize it to the physical geometry, I can get it much higher than 1, and that is what effectively the cross section tells you. So that's a very convenient way of representing it. In this case, what you're seeing is that scattering cross section is exhibiting a increase. Basically, the overall scattering is increasing. So nanoparticle size increases, it's scattering better. That kind of makes an intuitive sense. And also, the resonant frequency is redshifting. Why does the redshift happen? Okay. The way you can think about it is that, let's say if I have a nanoparticle of this size, I'm talking about this induced dipoles, right? Now, as the size of the nanoparticle increases, as let's say I'll call this as, let's say, d diameter. Okay. As d increases, my dipole, the restoring force, right? So restoring force, F restoring, decreases. Okay, effectively, right? Because the charges are farther apart. So the attraction, Coulombic attraction decreases. And because of that, if you look at the resonant frequency, we have seen that for a simple harmonic oscillator, it will be K by M, wherein K is the spring constant, which is capturing the restoring force. So now effectively, my spring constant K is reducing, right? Since my restoring force is decreasing, my K reduces, therefore my omega reduce. This is if I call it as omega naught. I just want to capture that. So omega naught reduces. The frequency of the resonance reduces. That means in wavelength, it redshifts, increases. Okay, it goes towards the red. That's why we call it as redshift. So you see, as the size of the nanoparticle is increased, there is a redshift in the resonance, and it is also serving as a better scattering particle, better scatterer rather. Okay. So what is that all? Well, conveniently, I have plotted what is known as a dipole mode in the case of a nanoparticle here on the left. But if you look at the total cross section, scattering cross section of a nanoparticle using Mee theory, you will see that there is this shift, which is basically because the dipole is shifting in the red into the red. And also as the size of the nanoparticle increases, there are these higher order modes that are coming in. So this is basically the higher order mode. In this case, this is what is known as a quadruple mode, higher order mode that comes in. And then you see one more peak that is coming out. All right. So this is what happens when you increase the size of the nanoparticle. So, okay, in the spectrum it is increasing, but physically what is happening as I increase the nanoparticle? All right. To look at that, let's look at how the electric fields look like. So again, using Mee theory, we have calculated this. So basically this is on the left, this is what we call as electric dipole mode for a nanoparticle, which is, I think, diameter is 50 nanometers. If I'm not mistaken, let's see. This is my line. This is, yeah, roughly 50 nanometers. And then I have another electric dipole mode, which is for an electric dipole. D is basically, in this case, 150 nanometers. And this is my quadrupole mode, electric quadrupole. D equal to 150 nanometers. So what you are seeing on the plot is the electric field intensity. More specifically, it is the electric field in the x direction at the resonant wavelength. So for example, if you look at a 50 nanometer nanoparticle, you have this peak here. So at 365 nanometers, we have seen the electric field. And how does it look like? Well, you see that the electric field is confined close to the edges. Why is this happening? So if you look back in the electrostatics, you will see that we had this nanoparticle and we kept on talking about this positive and negative charges which are accumulating, right? And if you look at the field lines, we can actually draw them. The field lines, look, let's say consider a nanoparticle in a constant electric field, okay, uniform electric field. If I think of that, I'll see that if I were to draw the electric field lines, they'll look something like this. You know, I have my field lines which are coming into the nanoparticle here at the negative side, and on the positive, it keeps going out. So, but if you go far away from the nanoparticle, you will see that the electric field lines are not disturbed very much. If you go very, very far, they are more or less undisturbed. So you see like this. So effectively, this is my physical dimension, the cross section of my nanoparticle. So it's a circular shape. So I can pi r square, or the d is the diameter. So I can calculate what is the cross section. Even though the physical cross section is small, at resonance, because of the strong polarization that is happening, the nanoparticle behaves as if it's much bigger. So this is my actual, if I were to compute, I can think of scattering cross section which is larger than the physical dimension, right? Scattering CS cross section, okay? And now at resonance, we are seeing that there's a lot of charge accumulation that is happening. That means, how do we represent that in terms of fields? Well, we actually draw denser electric fields, right? When you have a lot of charge, you will have to have more denser electric field, and denser electric field means that the intensity is larger, and that is what you are seeing here. Electric field is stronger here on the edges. So this is what we call as a dipole mode. So the charge is on the plus and minus. This is a dipolar mode, what we call as. And now what happens to this dipolar mode as you increase in size? Well, the similar behavior is maintained. The field profiles look similar. So we conclude that, okay, at even 455 nanometers, for example, this is 150. So this is roughly here. At 455 nanometers, my electric field is looking like this. So it is like a dipole. And what happens at this lambda of 367 at 150 nanometer diameter? You see this additional peak that has come in. And that additional peak is what we call as quadrupole, because instead of plus and minus, now you have plus, minus, minus, plus, minus. So there are 4 of these charges effectively. Okay, and that is why we call it as a quadrupole instead of a dipole. And you can also have higher order terms, which is octopole and so on. Well, the field depends, field lines, field intensity distributions become more complicated. All right. So basically, this is what happens as you increase the size of the nanoparticle. The field is redshifting, the resonance is redshifting, okay? And the field lines exhibit a characteristic dipolar behavior. And as the particle becomes much, much larger, the higher order modes, and right now it's quadrupole, you can even have octopoles and all coming in, all right? This is what we'll observe. Yeah, Saurabh, you have a question?
Why is the resonance broadening?
Well, why is the resonance broadening? Well, it turns out that as the size of the particle increases, it is actually able to scatter more efficiently, or more scattering. So the losses are more. The scattering loss is more, so the resonance is broader. If you actually compute the amount of joule losses for these things, it is not that much significant. Okay, you can actually, using me theory, we can compute. Basically, you can compute what is known as sigma. I can call it as cross section. So I'll call as absorption cross section plus scattering cross section. I can compute what is known as extinction cross section. Okay, extinction is the total amount of energy that is lost. Absorption plus scattering is called as extinction. So I can compute these things, and if I specifically look at what is this absorption cross section, I'll see that the absorption cross section is not that significantly broadened, but it's just that the scattering losses are high, and therefore the resonance is becoming broader. Well, this is as the size of the nanoparticle increases. What happens as you reduce the size of the nanoparticle? Well, for that, what you see is, this is a graph that I have taken from this book. You can go back and look at that. So essentially, this is the absorption. Of course, this is taken in a solution of nanoparticles dispersed in, let's say, water. We'll talk about it in the next lecture, what happens when you have changed the medium. But effectively, what you see is that the absorption through that dispersion of nanoparticles is actually it's becoming broader as the size of the nanoparticle decreases. So for example, this is 2R, the diameter initially 9.2 down to 2.2. As you reduce the size, you see that the absorption is becoming broader. Why does that happen? Well, so far when we considered the metal properties, we talked of omega p and gamma. Gamma was a loss parameter, right? These are material parameters. Material parameters. And depending on the metal, we know what it is, right? So that's what we thought. But it turns out that when you have, let's say, a nanoparticle of some size like this, the electrons are moving. In response to light, the electrons are moving, but they just don't move only. I mean, they even scatter with the surface. You can have multiple scattering at the surfaces and so on. When this scattering happens, so basically here electrons scatter at surfaces, and essentially this scattering reduces the lifetime, between two events, and because of that the losses increase. Okay, so instead of gamma being purely an material parameter, it turns out that I can write gamma as basically a function of the radius of the particle. Okay, and if the radius is quite small, what happens is I can have the initial gamma naught, which is my material loss, plus there is a basically this A is a constant. You can they call it a phenomenological constant, essentially to capture the scattering mechanism. Okay, scattering, let's say I'll call it scattering mechanism dependent constant. For example, is a roughness parameter, how much is that, and so on, you can compute. And then Vf is a Fermi velocity. So basically electrons move in a solid with some Fermi velocity. So depending on the velocity, you can actually compute the rate. So gamma is the scattering rate. So basically I should have per unit time. So essentially this is a dimensionless constant, Fermi velocity, so meters per second, and then this is the radius, which is meters effectively, so per second. So effectively this whole thing becomes per second unit. So what you see is if you go to very small diameters, this becomes significant, and then the loss increases, and that's why the broadening happens. But let's say if you go to above 50 nanometers and so on, this size dependence, rather, basically if I go to larger particles, let's say size dependence insignificant at large R. Okay, but at large R, the resonance is shifting because of other parameters, but in smaller scale the resonance becomes broader. So effectively you cannot have a scenario that if you go to small nanoparticles, I'll have a very, very sharp. So if you looked at this picture, as I increase my diameter, the resonance is becoming broader, so I'll actually go smaller and smaller, I'll get a very sharp resonance. The idea, it turns out that if you have a very sharp resonance, that can have a lot of applications. So we always try to engineer that. So it turns out that if you go to very small nanoparticles of, let's say, 2 nanometers and so on, again the resonance becomes weak, the absorption is very small. All right. So this concludes my discussion on the size dependent parameters. So in the next lecture, I'll talk about how do we engineer these resonances and what are they useful for. Okay, so we have given the basic idea of what it is. We will also talk about the applications in the next part, and then once I finish that, I'll conclude the discussion on the localized surface plasmons, and then we will move towards what are known as propagating surface plasmons, SPPs. Okay, and plasmonics is a very broad area, and what I'm trying to do is I'm trying to give you a glimpse of it. I mean, we can actually have a full semester course on that, talking about various details and so on. Well, that is not the idea for this course. So I'm trying to give you the fundamental ideas which are useful broadly in many, many different places. Okay. All right. With that, I'll conclude. Any questions? All right. Thank you so much, and I'll see you in the next lecture. Bye.